Now we're going to take a look at what we call second order partial derivatives. Just as we have second derivatives and third derivatives and so on when we have a single variable input, we also have higher order partial derivatives. So let's take a look at what the notation might look like. If we are given a function, let's say f of x, y, and z, there are a few ways to denote a second order partial derivative. Now, the first way is a subscript notation, and they're always written left to right. For example, I can write f with a subscript of x. That would be the first order derivative with respect to x. And if I put a second x beside it, that means we want to take it again with respect to x. Now we can also write, let's say, f of x as our first derivative, but then take the second derivative with respect to y. What that means is that we are going to take the first derivative with respect to x, and then we'll take the partial derivative again with respect to y. In other words, the first derivative with x and the second derivative with y. So in the subscript notation, that means we are going to go in order from left to right. And if we're using the subscript notation along with Leibniz notation, that means we're going to work from the inside, find the first derivative with x first, and then move to the outside, find the partial derivative with respect to y. Now let's take a look at example E. We're going to consider the function f of xy that equals 3x squared minus 5x cubed y squared plus 2y squared. We want to find the following. Well, let's take a look at the first derivatives to begin with. Here on the left, we want to take the derivative of f with respect to x. So that would give us a 6x minus a 15x squared y squared. Remember, when it's attached, that constant comes along for the ride. But that third term, the 2y squared, is treated like a single constant, so it would be 0. Over here on the right-hand side, we're going to take the derivative with respect to y. So our first term, 3x squared, is like a constant. It's 0. The second term, we multiply the negative 5 by the 2, we'll get a negative 10. X cubed stays the same, y to the first. And then the last term would be a plus 4y. So on the bottom, we're going to be taking the second order partial derivatives. So here on the left, we have f of x and x. So we're going to look at this first derivative on the left, and we're going to take the derivative again with respect to x. So that would give us a 6 minus 30x y squared. The next block, it asks for f of y and then y. So we're going to use this derivative, where the first derivative is y, and we're going to take the derivative again using y. So that's going to leave us with a negative 10x cubed plus 4. So in the next block, we have a second order derivative where the first derivative is with x and the second derivative is with y. So we're going to use f sub x. And if we take the derivative of that function with y, we would get a negative 30, x squared stays the same, and then y to the first. With the last block, the first derivative is with y, so we're going to use this guy and now take the derivative with respect to x. So we would get a 30 x squared y, and then the 4y becomes a 0. One of the things that you might notice is that the partial derivative, xy, and the partial second order derivative yx has the same output. In other words, the second order partial derivative of xy equals the second order partial derivative of yx. This is always true for continuous functions with two input variables. Now let's look at Leibniz ratio notation. Now the derivatives here are taken in the opposite order that they are written in. In other words, they go from right to left. Well, let's first take a look. If we have a partial derivative, they may say squared with respect to f. In other words, that's representing like a double prime, means we're taking the second order partial derivative. But if it's an x and an x, they're going to use an x squared. So notice how those squares are in different places. One is right after the partial derivative of d, and the other one is after the variable. So this means the same thing as the second partial derivative of f with respect to x, and again with respect to x. However, if we're dealing with two different variables, in other words, we are taking the second derivative, the second partial order derivative, if we do it with respect to x and with respect to y, the order is backwards. It goes from right to left. This would mean the same thing as taking the first order partial derivative with respect to y, and then taking the partial derivative of that function again, but with respect to x. Let's take a look at example f, where we have the function f of xy equals 5x squared minus 2x squared y cubed minus 7y squared. In the top first block, we are taking the first order derivative with respect to x. So that will give us a 10x minus 4x y cubed. And then the second block to the right, we're taking the first order partial derivative with respect to y. So we would go to the second term and get a negative 6x squared y squared minus 14y. So in the bottom row, we are finding the second order derivatives. So in the first block, we're taking it with respect to x and then with respect to x again. So we would use this block, and with respect to x, we would get 10 minus 4y cubed. In the second block, second order derivative, but doing y twice. So here's y the first time. And if we take the derivative with respect to y again, we would get a negative 12x squared y minus 14. And in the third block, remember it goes in the opposite order in this notation. So here we're going to use the y first, and now do it again with respect to x. We would get a negative 12x y squared. Also note, if we were to do the second partial derivative, where we did the y second and the x first, looking at this derivative over here, that x, if we did that in terms of y, we would also get the negative 12x y squared. So the same is true regardless of the notation. The second order derivative, it does not matter which variable you do first. If you do the x first, then the y, or the y first and then the x, you should get the same result, as long as the function is continuous.